Alright, welcome to another video on electronic circuits, and today we're going to be making a little review of what series and parallel resistors look like. So essentially imagine that you have a bunch of resistors in series, something like that. So let's call this one R1, R2 and R3. Now suppose that the voltage or the total voltage difference or the potential difference between the two ends is given by V, or let's call it V in. Then we want to know what exactly is going to be the current flowing through the whole circuit. Now the rule of thumb is that the current is the same for resistors in series, so the current doesn't actually change at all. The current is going to be the same across each one. So what we can do is we can say, okay, so let's have a total resistance which is going to be equal to the sum of all the resistances, R2 and R3. And we can usually denote that by a more common kind of notation, which is your sigma R, or the sum of all the resistances. Normally you can put a little subscript, but this is enough to understand that it is just the sum of the resistance across circuit. So then what we can do is we can say, okay, we can use Ohm's law, which is V equals Ri. And in this case, we can just rearrange that so that the current is going to be given by V in divided by the total resistance, which is going to be just the sum of the resistances. So to give you an example, suppose we have a circuit that looks like this. So let's have a DC voltage supply of 10 volts, and then let's have a resistance of 1 kilo ohm on each of these ones, and we want to find out the total current. Then what we can do in this case is simply say, okay, so the total resistance is going to be the sum, which is just 3 kilo ohms, and then to find the current through the circuit, we're just going to have the voltage, which is 10 volts, divided by the 3 kilo ohms, and that's going to give us about 3.33 milliamps, because we're dividing volts by kilo ohms, and that's going to give us the answer in milliamps. And the other thing we can do, of course, is we can find the potential drop across each of these resistors. So essentially, if we call this one 1, 2, and 3, we can find the potential drop across resistor 1, which is just going to be this times 1, and that's going to be 3.33 volts. And in fact, because all the resistors are the same, all the potential drops are going to be essentially the same. So we're going to have 3.3 volts, and then that's going to be equal to the potential drop across resistor 3, which is this one. And that obeys Kirchhoff's laws, because we know that all of these voltages are going to add up to 10 volts. So that's essentially it. So the things to take away from this is that when you have resistors in series, essentially the current does not change. The current is the same for each element on that circuit, but the voltage actually changes. There's going to be a potential drop across each of those resistors. And that's basically it. Now we can do the same. We can start looking at things in parallel. So if we have a bunch of resistors, suppose we have a potential difference that once again we're going to call voltage in, and then assume we have a bunch of resistors like this. Alright, so we have R1, R2, and R3. Then the rule is that the total resistance is going to be equal to the sum of the reciprocals. So essentially we're going to have R1 plus 1 over R2 plus 1 over R3. And that's going to be equal to the sum of 1 over the resistance. And now the next thing we can do is we can say, okay, so we actually want to find out this. So we want to find R total. But that doesn't mean that we're going to flip each of these ones, because that's not how algebra works. So what we need to do is we essentially take this expression and we're just going to raise it to the power of 1 minus 1. So that's the same as saying 1 over R1 plus 1 over R2 plus so on to the power of minus 1. So we calculate this whole thing first, and then we basically take the inverse of that, and that's going to give us the total resistance, or the equivalent resistance for resistors in parallel. And that's basically it. A very important case that we need to look at is when we have two resistors in parallel, just two of them. So R1 and R2, and then plus and minus, some input voltage, something like that. Then in that case, the total resistance is going to be given by 1 over R1 plus 1 over R2 to the power of minus 1. Now we can add these two fractions, so we're going to have R1 times R2, and then over here we're going to have R1 plus R2, and all of that to the power of minus 1, which means we're going to flip this over, and that's going to be R1 times R2 divided by R1 plus R2. And this is a very, very important kind of result because it is used very widely. In general, you won't have, there aren't many situations in which you will have more than 2 resistors in parallel, and usually you can break things down into smaller kind of circuits. So this is a very important thing that we need to use. And in general, what we can use is we can use this shorthand notation that basically means that we have 2 resistors in parallel, and this basically amounts to this formula. So it is like a shorthand notation for that. So to give you an example, we can combine resistors in series and parallel into another circuit. So suppose we have something like this. So we're going to have R1, then another one over here, R2, and then let's have something that looks like this, R3 and R4. And we want to find out essentially the equivalent resistance for this whole thing here. Then what we would do it first is starting from this side, and I'm actually going to do this in a different color so you can see it more clearly. We're going to grab these 2 resistors, and they're in series, so the equivalent resistance at that point is simply going to be R3 plus R4. And then basically from that, we know, okay, so that's the equivalent resistance over here. Now we're going to take this value, so that's the first step. Second step is going to be, this is going to be in parallel to this one. So the equivalent resistance for this whole section here, which is the green one, is going to be as follows. So we're going to have R2 in parallel with R3 and R4. Okay, so that's essentially what we're going to have. So, and then the last one is going to be R1 including this. R1 is in parallel with this total resistance over here. So R1 in parallel with R2, which is in itself parallel to R3 plus R4. So this is kind of the shorthand notation that we would use to represent the total equivalent resistance of this circuit, which we can call R total or R equivalent, whatever you want. And that's essentially how we represent that. So if we break it down, let's look at this section over here first. So R2 parallel with R3 plus R4. So basically we can just use the formula which is given here. In this case we have R2 times this resistance, which is R3 plus R4. And then we're going to have R2 plus this, which is going to be R2 plus R3 plus R4. So that's going to be our total resistance over here. And then if we take the resistance parallel to that one, so that's going to be R1 parallel to this whole thing, then that's going to be R1 times this whole thing, which is going to be R2, R3 plus R4, divided by R2 plus R3 plus R4. And then that's going to be divided into, or it's going to be divided by the following. So we're going to have R1 plus this whole thing, so the entire resistance, which is R2, then R3 plus R4, and then divided by the sum of all those resistors plus R3 plus R4. And we can see that we can essentially construct any equivalent resistance by using these basic principles. Now, there are rules for capacitors and inductors as well, and this is something that we're going to explore in the next video. But for now, this is basically what you need to know. This is how you add resistances together, and this is quite useful because it is used in a lot of applications. Most circuits that we're going to deal with in electronics are going to have a lot of resistors in them, so it is important to know how to evaluate these things to find things like voltages and currents and so on.